Section 5.6, Apparent Weightlessness and Artificial Gravity. This is the ideas that we've already seen in the previous sections. So we can imagine for a moment if you are living on board an orbiting satellite. Does that mean you're weightless? Well, let's take a closer look to investigate this. So, a conceptual example here, apparent weightlessness and freefall. When a person is standing stationary on the Earth, his weight is 800 newtons. Consider the person on a scale in a freely falling elevator and a satellite in circular orbit. In each case, what is the weight recorded by the scale? I'm going to let you read through the options and choose one. And when you have decided on one, you can go on in the video. So go ahead and pause now. Right, so we've previously seen this one, and we saw that when the elevator chain breaks, if the man starts freely falling, as does the elevator around him, then while they're in free fall, the man can't push on the scale to have it show any weight. And so it ends up being, he appears weightless, right? There's nothing on the scale there. What about the circular orbit? Well, in this case, the man and the satellite are feeling a force towards the Earth, and there's no normal force. There's nothing pushing back to keep them up. The only reason they don't crash into the Earth is they have this large amount of velocity going sideways. So even though they're falling towards the Earth, the Earth keeps moving away from them. And so it creates this interesting circular path. But even in the satellite is constantly falling. It's in constant free fall. And so both scales are going to record 0 newtons. It's a way to be weightless, is to just be in orbit like that, which is pretty wild to consider. On the flip side, because being weightless can have biological effects that are detrimental, especially over time, there's a lot of work being done to consider how to create artificial gravity. And one possible way to do this is to create a space station that's rotating. Because as it rotates, then it can create this inward centripetal force that mimics that of gravity. So you may have seen this before on a carnival ride like the Gravitron, right? Usually people just stand up and get pressed against the wall, and then it tips and you're still pressed against the wall. But you can potentially stand up and it's as though you're standing upright because of the spinning effect. So you can ride the Gravitron like a boss. I claim no liability if you try this and get in trouble, right? So please maybe don't actually try this, but it does apparently work. I mean, based on the science, and we could calculate it for a given scenario. So let's look at this example of artificial gravity. At what speed must the surface of the space station move so that the astronaut experiences a push on his feet equal to his weight on Earth? The radius is 1,700 meters. All right, so we're given the radius here, and we know that it's going to be turning, so we're going to start thinking about our centripetal acceleration. That's creating this inward centripetal force. And what's generating that centripetal force? Well, what's creating this inward force is actually the normal force. But we want this normal force to be pushing back exactly the same as if the person was standing on Earth. So that means, in other words, we want to set the normal force so that it's equal to the weight of the person, or equal to mg. So that's our key. So now we can take a look at how to do this. And if you want, you can go ahead and try this, see how far you can get, and then compare with the answer in just a moment. Okay? I'm going to move on now, but you can pause. So if we take a look at this centripetal force, which we know is just the net force that is acting in that particular direction, we want that to be equal to mass times the centripetal acceleration, AC, and we want that it's going to be created by the normal force. So I'm going to fill in my normal force here. That is the net force that is acting on the person. There's no actual gravity pulling them down, but there's a normal force as though there is gravity pulling them down. So then in place of the normal force, we can substitute in the weight, mg, and set that equal to mv squared over r. Once again, the masses are going to cancel. It's very convenient. And we can solve for v by multiplying the r across and taking the square root. And we end up with this pretty simple expression that the speed of the space station needs to be rotating at the square root of the radius of it times whatever acceleration we want the person to experience at their feet. 9.8 meters per second squared if we want to be exactly like Earth. And so then we can calculate that that would have to be moving at 130 meters per second. But that's only if we want it to be exactly the same as Earth, right? It would be very possible to say, hey, we just want the normal force to be something else, right? Maybe it doesn't need to equal the astronaut's actual weight. Maybe it's just some fraction of their weight. You'll get to try that out on a homework problem. So I'll leave that for you. But this example pulls us through the end of chapter 5. We have now come full circle in studying uniform circular motion and how the circles work when you start moving in a circle. Thanks, y'all.